welcome everyone to our final webinar of the series of 5 webinars regarding functional safety. As I mentioned in the very beginning, it's our series of 5 webinars where we will be looking into different elements, I would say, of functional safety, from introduction to looking into processes, tools, and stuff like that. So, and now we want to talk a little bit about, the practical side of things. So, namely, some complex stuff that nobody really want to talk about. So, like formulas, like complex, a bit more complex equations than we normally used to. So that's what we're gonna talk about today. So what is our agenda for today? Well, first of all, we'll be talking about some practical quantitative measures that we normally use during the functional safety projects and designing functional safety products. We'll be talking about actually setting safety targets and why it's important. Then we'll be talking about failure rate metrics, diagnostic coverage and fault tolerances. Also, we will touch upon demand mode and calculations related to that. We'll be talking about calculation of safe failure fraction. And then if any of you brought any example that you would want to, to crunch, then we'll be ready to kind of discuss the auditory case, and then also maybe touch very fast on the common pitfalls. So that's what we're going to cover today. And just to remind all of us that we have been going through 4 topics on functional safety webinars until now. And the first one was introduction. Then we were talking about how to architect the functional safety product. In webinar number 3, we touched upon processes related to functional safety products development. And on our previous webinar, we have been looking into tools, tricks, and different recommendations on how to actually make the development of functional safe products a bit more cozy, a bit more practical and enabled in the organizations. So today we are concluding our 5th webinar, and I think we are ready to move on. So today we'll be, like always, having 2 presenters. First one is me, Alexander Lubimov. I'm Business Director in EKTOS Development, leading customer relationship management, and also onboarding our clients into, into the development projects with us. So, and please welcome my colleague Vadim Dogopoli, who is waving his hand, who is, first of all, our technical solution architect, and also our top class expert in functional safety products development. So we'll be, like before, doing this webinar together. So let's move on. So first thing what I want to mention is that, well, we have been covering quite a few topics until now. We have been looking into process, we have been looking into architecturing functional safety, we have been looking into tools and tricks and all practical, I would say, advices what to do. And well, at least for me, during the last webinar, I had really good feeling, like, okay, it seems that we have been covering the whole thing, the whole kind of landscape of what is needed to be able to make the functional products development. So basically, is it right? Well, it is right. We need the right processes, so we need to go to right results, correct. We need to have right design, so we are not facing any challenges with the product later on. Yes, that's also right. Tools, super important, and they lead to effective result. That's okay. And then we need to have right skills and knowledge. So this is kind of obvious. Of course, we need to have a strong team and knowledge to be able to run the development of those functional safe products. So, but that's all right. That's all correct. We're just This is super important to have, but at the same time, we have actually a quantitative part of the game, which is not that fruitful to address at first place. And why we need this quantitative part of the development process? Well, first of all, we do have some requirements to quantitative part, and we will be covering those a little bit later in the presentation. Secondly, actually, if we cannot prove and generate so-called quantitative evidences, we cannot actually defend our safety case. So it's really important to understand that quantitative evidences, they are like hard artifacts, hard in terms of explainable, in terms of defendable artifacts we need to create when we actually do functional safety products development. The other thing what I want to stress is that basically the quantitative approach, when we can measure something, allows us to compare different designs, different architectures, and different ways of solving our functional safety design in the customer product. So we can actually compare and reach to the good enough level instead of doing everything what leads us to the best potential result, because best potential result has its own cost, apparently. So what is important is that we kind of right at the spot where we want to be with our quantitative metrics, so we are not over making the project. So this is super important because in functional safety projects you have so many complications around, and if you kind of apply too much pessimistic approach, so you want to be on the safe side with all the metrics and do only best in the development, then the cost of that project will be extraordinarily high. So that is important to remember. So, and how actually, like I mentioned, we do have some metrics, we do have some requirements in functional safety projects that are called, safety targets in terms of quantitative approach. And why those safety targets exist? First of all, there are some application standards. The application standards are normally prescribing required safety integrity level. So and apparently we need to comply to that if we want to claim that we do have a specific safety integrity level in place. So you can see some of the standards like machinery 13849. Then we have 15194 for e-bikes we have been working with recently, and EX 6061 for medical electrical equipment. So those standards, they actually prescribe or may prescribe for your specific product some safety targets. And those standards, they may define mandatory safety functions that are derived from industry knowledge, so to say. And those standards can also define minimum performance levels and safety integrity levels. So that's the way it works. Second pillar or second part where requirements come from to the quantitative parts is first of all our customers, some of you who are joining us today, where you have business or market requirements. So let's say we want to develop a very solid e-bike, and we know that the best e-bike on the market we want to compete with is done by whoever, by BMW. So we want to compete with BMW in terms of safety. So then what we do, we can see in the specification of BMW's e-bike the performance level, safety integrity level they declare, and then we can say, okay, in our specification for the product we want to be at least as the BMW reference e-bike. So this is how normally sales and marketing teams are bringing based on the competition analysis, they're bringing those requirements into the product development. So, and apparently it's of course very important that we also consider the relevance of those requirements, because the relevance of safety requirements, of course, relevant for the safety functions. So it's not, we need to, to put it short, we need to analyze it pretty carefully, so we're not overcomplicating stuff. And the third part, where those measures in terms of safety targets come in, is hazard and risk analysis, because based on those hazards and risk analysis activities we normally do during the product analysis and pre-architecture and architecture phases, they actually declare what is the minimum safety target we can put to be able to reach specific performance levels and stuff like that. So these are the three directions where we get our safety targets from. So what are the most used calculations we have to do to work with our safety targets? There are pretty few, and we basically listed all of these most used calculations. So we do have two. First ones are probably the most used ones during the certification. That's probability of dangerous failure demand, the average one, and profitability of dangerous failure per hour. So these are the two major ones that are used to basically defend your safety case. Then apparently, to start with, you have failure in time. That is normally based on the failure rate, which is well known as lambda variable. So that's normally what you kind of base your calculations on. Then we have something called probability of failure in mission time, that basically comes up with the probability of failure during the entire time of our mission or operation in that regard. Then we have dangerous failure rate, like amount of failures per hour, mean time to dangerous failure, so-called MTTF, diagnostic coverage to understand what is kind of good enough to diagnose, and how we can actually come up with this measure, say failure fraction, hardware fault tolerance, and also the so-called proof test interval, its duration or its frequency. So these are the calculations we'll be covering today in our presentation. And basically, it's a good, kind of how-to for you to, to get your hands dirty with the calculations related to functional safety. So to start with, I want to actually demonstrate, the so-called failure in time thing, which is normally derived from, I would say, two potential sources. First potential source is safety manual for the components that are already pre-certified or certified. So if you have a component in your system that actually has safety certificate, apparently from the safety manual on that component, you can actually get this FIT value. And that FIT value is calculated extremely simple because it allows us to get actually our lambda multiplied by 10 powered by 9. And I think that's extremely simple to do this calculation. Then we can also, from that, we can derive from our requirement specification the mission time that we normally calculate from the application. And then we, by having these two based on FIT and requirements, we can also calculate the probability of failure. So, and here on the right side, I'm basically demonstrating to you, please mind you that this is logarithmic scale. This is the visual comparison between, the mission time duration here on the X axis and the probability of failure on the Y axis, measured for different failure in time characteristics, so to say. So you can see how different these values could be for different failure in time parameters. And to visualize it a little bit more, I can demonstrate, because many of us know that normally in functional safe projects, you have to solve safety functions by implementing redundancy. I want to demonstrate how it looks when we approach our architectural safety function redundancy by using 1 out of 2 redundancy schema. How different the FIT basically and reliability improvement looks like. So you can see the single, for instance, we have 2 sensors or 2 objects just being in a safety function. So you can see the one in this way sensor gives us the yellow line of reliability basically, and the blue one is what we get when we have a duplication in a redundant manner by 1 out of 2 redundancy. So you can obviously see that the probability of failure here is getting way lower if you compare these 2 lines by the y-axis here. So and you can see how it gets a little bit more closer to each other with the mission time duration. So that's the visual kind of demonstration how these calculations can affect your understanding of reliability improvement. So and now I want to pass microphone to Vadim, who will explain us a little bit more tricky calculations. The floor is yours, Vadim.
Yeah, thank you, Alexander. Yeah, just before diving in metrics and to see how it is calculated, I want to say that the very good guidelines are presented in the standards, how to calculate exactly with formula, with examples. And our goal now is to bring them most useful and explain what these metrics means and how to use them and how to understand them in real life and what you can face developing functional safety. Before doing this, we have to look into demand mode for application. And for this, we have low demand mode and high demand or continuous mode. And it says how frequently functional safety will work in your system. 6158 define low demand as a safety function which operates less than 1 time per year. So you can imagine emergency shutdown button on chemical reactor or any other type of reactors. You can imagine it in ideal world it will never work if everything is okay. We consider this as low demand because person can press this button. This very rare event. And the opposite side is high demand or continuous demand, something which operates much more frequently. So if you're talking about e-bike control, it means that you are driving and all the time when you release a throttle or you stop pedaling, motor should be disabled. So it means that it could operate each minute, each second, or all the time during operation. So it's called continuous demand or high demand. And specifically for instance, for machinery, only continuous demand is considered. There is no notion like low demand, because obviously it all the time operates and all the time creates dangerous and safety functions operates all the time. Okay, knowing the demand, there is 2 different metrics, and it is the main metrics what you need to meet. In fact, functional safety leads to only to one of these 2 parameters, depending on your demand, and rest of them is to calculate this or derive from this one of these 2 parameters. For low demand, it is used probability of dangerous failure on demand. Here we are more interested in what is the probability of activation or operation of safety function when we need it. So and event of need of this safety function. For example, like emergency shutdown valve. So we're not we are interested. So if we need to close this valve or open this valve, what's the probability at the time to open this valve or close, depending on your application. And this valve can operate never or maybe a few times or entire mission. And for this we are using probability. But if we're talking about continuous or high demand, we are using a frequency of failures or probability of dangerous failure per hour. Here we are more interested in how much faults can occur can happen during operational time or in hour or in some short period of time in comparison with mission time. And if we're using continuous demand, we are going to failure rate here. And this is one of two metrics we have to apply to our system. Yeah, and inputs for these key metrics is mean time to failure or mean time to dangerous failure, just to be more precise. It shows how much time before dangerous failure occurs, present in this one, and yeah, and reciprocal value is lambda d, which is usually used in 61508, and MTBF is used in machinery standard. It is just the same idea, but just different view of this. So in one time we are showing time in hours. In for 61508 we are demonstrating a frequency of dangerous failure. And another important thing is diagnostic coverage or safe failure fraction, depending on safety integrity level. And usually in the standards it's divided like low, medium, high. So there is no specific values, or specifically on the beginning. If you start in your project, you need only to define like 3 levels for this one. And during FEMIDA you can calculate this more detailed. And to get this values or to metrics, we are going into our architecture design, where diagnostic described and failure mode and affected analysis perform, and we understand how we mitigate detected faults, and taking our hardware design, taking component by component, resistor by resistor, capacitor by capacitor, and simulating their faults, we calculate lambda or MTBF, and also defining how much fraction of safe failures in our design. I mean, based on real calculations, and same for diagnostic coverage. So diagnostic coverage on the beginning, we are selecting them by low, medium, high, and when we are going before starting FEMIDA, and after FEMIDA, we can get exact value of this diagnostic coverage or safe failure fraction. Yeah, here it is about these numbers. What means safe failure fraction? So if we have different type of faults and we have diagnostics, we can split all faults in 4 categories. It is safe detected and safe undetected, dangerous detected and dangerous undetected. And our main goal is to reduce the number of dangerous undetected faults. And the idea that we can convert dangerous detected to safe. So if we can detect a fault, we can transit the system to the safe state, and in this way we are converting system to the safe state and converting the dangerous to safe. And a safe failure fraction, it is how many failures are either safe or detected and converted to the safe before they can cause a hazard. So, and of course, a higher safe failure fraction means the better diagnostics and the less dangerous fault in the system, probability of dangerous fault. And here you can see that diagnostic coverage defined in different way for machinery and for system safety. For machinery, low diagnostic coverage means if you below 60, medium between 60 and 90, and high if it is higher than 90%. But if we go into EEC 61508, it says that lower diagnostic is between 60 90, medium is between 90 99, and high is 99. So you have to be careful when you are working with the standard. It could be confusing just to be sure that you are, if we are talking about we need medium diagnostic coverage, it is the same medium what standard says here. Okay, the next metric is hardware fault tolerance. It is ability of system to continue to perform safety function having fault. So if you have hardware fault tolerance 1, it means that even having one fault, the system still can perform its safety function. So if you have 0, any fault, any dangerous fault, means that it will be dangerous. Machinery standard describe 5 categories, and I try to link them with fault tolerance. Category B or 1, it is one channel where you have input, logic solver, and output, and it has HFT 0 equals 0. Category 2, it is when you have one channel plus diagnostic. It can detect, it is much better than category B or 1, and could provide safe state when fault is detected, but still dangerous fault is not covered here. The category 3 and 4 can withstand one dangerous fault because you have 2 independent channel, and if dangerous fault occurs in one channel, another one can still keep operate correctly and can provide the safe state. Here it is from machinery standard. It is a good example how we can define the maximum performance level in different architecture categories according to this standard. For performance level in the Y-X left side, A is the minimum one, E is the maximum performance level. So here you can see that if you are using category B, it is very low safety integrity could be reached there. So, and the same for category 1. This is one channel, and what you can do, you can only increase mid time to dangerous failure, and the maximum level what you can reach is C, which is more or less okay for some application. For instance, for e-bike control, there is requirement C for performance level, and it is could be reached if you have very reliable equipment. So it is very simple, and simple components is used there. But I would say this is very difficult to reach to this level for this category. And if you have one channel in diagnostics, you can see the maximum level you can reach is D. And for this one, you need to again to play with different mid time to failure and performance level. you can reach the different level of the different performance level. And the best in the according to this standard is category 3 or 4 with different level of diagnostics and MTBF. Also, as you can see here, diagnostic coverage is also diagnostic coverage gives you ability to if you have high diagnostic coverage, it gives you higher performance level here. And on the beginning, starting developing this using this scheme, you can approximately identify what the architecture could be used here to reach the required performance level. So I think this is very good picture and technique to avoid overcomplication and to find the right architecture. Yeah, here it is proof test interval. If you does not matter how good your diagnostic is and how good your proof test is, you have to the mission time is limited. That does not matter what you want to do. Here it is proof test interval. It is interval between tests which you prove that your system works. So if you look for sensor, you can calibrate sensor and apply the high level of whatever physical parameter, which is gas concentration or pressure, and to see that this sensor can actuate the valve or the system, and it can operate as usual. So, and it means that after proof test, probability of failures goes down because you have tested this, and before the next test, the probability of dangerous failure rising. We can say linearly. In fact, this is not, but we can approximately say it is linear function. It is more conservative way. And all the time when you are doing proof tests, all the time the probability of low fraction of probability of dangerous failure which is not detected still there. And at some point the this total probability of failure will be rise, and at some period of time you have to perform end of mission of your equipment and go to or replace equipment with something new. So this is the idea of proof test. Yeah. Usually it is 12 months for sensor. Maybe it could be 6 months depending on what you calculate. So if you have very good or very low fit value or probability of dangerous failure, it means that you can do a more real proof test. If you have a bad or not good performance, you can do proof tests more frequently. And of course, it increases the price of service because someone should do this, and it costs money. From the other hand, developing with very low failure rate is also time consuming and also cost consuming work here. Yeah, this is an example of different architecture and their mean time to spurious failure. It is more used for system level when you need to. You're not interested only in dangerous faults, but also you are interested in any fault. So you are doing service, which of course includes proof tests, but just to avoid downtown the system, just to be sure that it works normally all the time. And sometimes he uses this metric for big system, because you want to prevent not only dangerous failures but any other failures, because it can stop your system and can lead to lose money, or most likely lose money. And you can see that system 2 out of 3 is works as quite good. other, and one out of one is the worst case scenario here to the spurious emission to the spurious failures. Yeah, and here it is very important thing here to understand that when we are specifically if you are component developer like sensor or valve, standards require some values of this metric, but you have to remember all the time that this time it is not for valve or for sensor or for solver. It is a metric for entire functional safety function. It includes sensor, logic, solver, and actuator. And usually distribution of or contribution of each component in the entire safety function is like presented here. For sensor, it is something like between 30 and 40%, depending on the sensor type. For the logic solver, it is something between 10 and 20%. So if you are developing controller for bike or for other stuff, you have to know that numbers should be divided divided by 10 or multiple by 10, depending on it is lambda or MTTF. And usually the weakest place in all this in any system it is actuators. Sometimes it could I say it is 40-60, but sometimes it could be even 70% of entire budget, and you have to distribute rest of the parameter on between sensor and logic solver. So, and it is important when you are developing sensor, you can usually you are talking about 35% or 30%, but if you can reach less, it means that in some applications when integrator will use your particular components, and if your competitor will be with lower or with better metric, sometimes it can fit because it is no way to use another sensor, or it needs to create more complicated scheme like two out of three, or even maybe more complicated. Yep. Okay, this is where we are, Alexander.
Thanks, Vadim. Yes, so basically, we know it was a little bit overwhelming with all the calculations and a lot of abbreviations this time, but this quantitative part Vadim just explained is extremely important, especially the last slide, Vadim, you were showing about, the safety budget and how it can lead to, especially for the components manufacturers, to be more attractive in terms of, more you consume from the failure budget, less fruitful you are for the integrator. So it's really important to to use this matrix as the kind of sellable, I would say, sellable feature of your product when you're working with the component. So basically, now we have been going through our 5 introductory webinars, and some of you may think that, well, we are very well equipped to do the safety projects, and you are, apparently. But I also must say that we have been only scratching the surface with some of this, advices and tools and tips and explanation of how stuff is done. But you are now in the club of functional safety capable engineers and managers, so I'm pretty sure that it gives pretty good overview of what to do and how to move on, and have a lingo that will help you to, first of all, be more competitive in terms of attracting either certification bodies, or explaining to your development team, or be part of the development team where the rest of the group can be more more powerful and more knowledgeable in the functional safety projects. So that's very good. So obviously, we can help you to move on from here. Now you have the common lingo with us, so we can address your functional safety project and help to navigate in the whole process, starting from standards and the processes around, look into the specific metrics and double check the way those are calculated. When we started this presentation, I explained about this, FAT metrics, and it's good when you can pick up the component that has the safety manual, so you can get like FAT from there. But if you need to calculate FAT from the discrete components, just kind of implementing the part of the circuitry, that can be a little cumbersome. And normally we use the military book for that, to be able to calculate, the MTBF and TTF and stuff like that. So that's also where we can help you to do so, and also be a sparring partner, so to say, to double check, to triple check all the calculations. So we are sure when we're approaching the design requirements that we are well set with all the required calculations. So, and obviously, we can help you to, to put up the processes, tools, and whatnots, and help you to compile the evidences, package, and safety case to move on and see how easy it can be, if the homework is done properly, how easy it can be to certify your product with the notified bodies. So that's what we can offer as a development team. So we'll be happy to crack some of the tough nuts in terms of your projects and needs. So you are welcome to contact us for any, I would say, help and advices or consultancy ad hoc. So now it's all from us. Thanks everyone for joining us today. Yeah, Sergey asked, he would like to say thank you for the webinars. Yeah, you're welcome. We will be soon introducing a new series of webinars with a bit less complicated topic. I really want to say thank you to all of you, and wish you a very great evening.
Bye.
Goodbye.
Thanks a lot. Goodbye.
Thank you. Bye-bye.